Well, another very common problem is a piece of coax, and so I've represented it here by a conductor of radius A and a outer conductor of radius B with a spacing in between. And we'd like to find the capacitance per unit length of the coax. What we do is we make very similar assumptions that the charge is uniformly distributed along each conductor, and we'll take it in terms of a linear charge density lambda. We don't have to worry about edge effects, would be, say, at the end of this piece of coax, because we're going to assume that it's infinitely long. We take a segment of length L, which I've shown here. So we're going to be talking about this part of the coax of length L. And I'm not going to go through the symmetry arguments. We've done that so often that I think I can just say that because of symmetry, we can take a concentric cylinder between A and B, so A and B, that's at radius S and of length L. We're taking inside here then a cylinder of radius S. Applying Gauss's law, we would have the integral of E dot ds, E between the two conductors, over a surface that has a radius S and a length L. If we look on the right-hand side of Gauss's law, we would have the Q enclosed over epsilon naught. This side, because of all the symmetry, is just going to be E times the area of S. So coming over here, that's the magnitude of E times capital S. So that's the left-hand side. The right-hand side is lambda L over epsilon naught, because this is the Q within the length L. Well, what is capital S, the area? It's just 2 pi s, which is the circumference at radius S times L at the radius S. Setting the two equal, we end up then with lambda over 2 pi epsilon naught S. And notice that this is going to have the charge divided by L. So we're going to need to remember that. And the E field is radial, and it's going to be in or out depending on the sign of lambda. Now we got to talk about the difference of potential. And I've just repeated this expression here. Let's not worry about the sign right now, because we can fix it if we get the wrong sign. This should be this kind of del. The delta V is equal to the integral of E dot dl from A to B, and in reality we should have put a minus sign there. Okay, so then we put in our E field right up here, and so we have an integral from the inner to outer cylinder radii over S. The only S dependence is this 1 over S here. So pulling the constants lambda over 2 pi epsilon out and doing the integral of ds over S, we end up with the natural log of B over A. This is the delta V. That'll go in this position of our equation, and then we have Q on top, but Q is just lambda times L. So putting in our delta V, which is right here, and our Q here, we can simplify. We're left with 2 pi epsilon naught times the length L divided by the log of this ratio here. L is important because there's an infinite length to this piece of coax. The capacitance of the whole thing would look infinite. But if we divide by L, then we get the capacitance per unit length, and we're left with 2 pi epsilon naught divided by this natural log of this ratio here. If you look at this, we only have geometric behavior. Here's the B, here's the A, and of course we have our epsilon naught. But this satisfies our condition for capital C. So now let's see what these look like. We're going to plot them. So here's our equation for the capacitance per unit length. This is actually what I did. I plotted from 0 to 5. X is our ratio, B over A. And I set the constant 2 pi epsilon naught equal to 1. So I'm just plotting 1 over log of x. Look what happens. It goes berserk at x equal 1. That's interesting. Well, remember that log of 1 is 0. So that's why this becomes crazy. An interesting thing, of course, is it changes sign when you go to smaller. So why are we not worried about this? Well, this is B over A, and B has to be greater than A to be a physical capacitor. So we really shouldn't show anything below 1. So I've just plotted it from 1 to some value 5. It blows up, so we're watching this side of the plot. It blows up, but as soon as we move out from this ratio being 1, so make it just be just a little bit larger than A, then we'll get a finite value. If A were fixed, you're letting B get larger and larger, the capacitance goes down, which is somewhat like the parallel plate capacitor. When we increase the spacing, then the capacitance went down. So just to come back to the sign, I just want to point out that C must be positive. We were lucky because it turned out that this is greater than 1, then C, this is C per unit length, and it's positive. So over here, C is positive if we end up with B over A for the log. If you take the log of, say, alpha over beta and switch the order, you just get a minus sign. So you might have had to use this if you somehow got the wrong ratios. For example, delta V. If you got the wrong order, you can fix it by using this trick here. I want to just point out that you don't have to have two conductors. You can still have a capacitance. And so we're going to consider just a shell of radius capital R that's a conductor. And suppose we put Q on that shell. We know that Q will distribute itself uniformly over this shell. And then if we want to find the E field out here, say, we can consider all this charge at the center of the sphere. Therefore, use just Q over R squared to get the field. And then the V, of course, will be related to 1 over R dependence. We'll use Gauss's law to calculate the E field. What that gives you, KQ over R squared, and it's in the R hat direction. So if this is positive charge, it'd be a radial E field with this magnitude here. So we take the other electrode of the capacitor to be the great electrode in the sky. What we mean by that is that it's a sphere at R equal infinity. Therefore, the potential difference between R equals infinity and R equals R is our line integral, which I show here. And so I have the integral from infinity to capital R, E dot dl. I put in my E field, this quantity here. I'm going to keep dr parallel to R, so we're just going to come in straight. So it'd be like this. We're coming in like that from infinity, right along the radius. And so therefore this is just equal to dr. This is unit length. Okay, so we put in our K and our Q, bring it outside, and we are integrating dr over R squared for these limits. Well, if you keep our minus sign out here, do the integral, you get a minus sign. Do the difference between the two endpoints of the integral. This would be minus KQ. Here's our minus 1 over R plus 1 over infinity. Well, this is equal to 0. The two minus signs cancel, and we end up with this expression for the change in potential. I think you could have written this down from the very beginning, but I just wanted to make sure we knew how to get the whole thing. So now we form the capacitance by taking Q over delta V. Here's our delta V, and so we just put Q over that quantity here. Remember, K is 1 over 4 pi epsilon naught, so it's denominator, so it comes upstairs, and we end up with the capacitance being just a constant that is related to the radius of the sphere. If we increase capital R, the capacitance increases, so the larger sphere can hold more charge for a given potential. So how do we charge it? If you consider that you have a point in the room that is a long distance away from this sphere, and so you have, say, walls that are grounded, and so you hook that up here, and then you put a battery here, like this, between that point and the sphere. It would charge up to this potential here. So if this is a battery of V, this capacitor, which this is one electrode of the capacitor, would charge up positive Q, and then the room walls, which are far away, would accept the minus Q. Now realize, if we consider that to be one big sphere, that minus Q would be distributed over the entire sphere, so the charge density could be considered very, very close to 0. This would have the charge Q on it. it is a clear-cut way of getting charge on here. Here's another way. You still have to have an idea of some surface at a very long distance, which is like a conductor. You walk in the room and you take the cat's fur and the rubber rod, charge up the rod, scrape it on the cylinder, and you put a plus Q on that charge. Actually, I picked the wrong thing. You want to use silk and glass, which will put a plus Q here. Okay, in that case then, you're back to what you had. You have a conductor that is very far away. You have a charge Q, and you were the battery. You provided the energy to put that charge Q onto this surface. The net result, though, is that this is the capacitance. So if you put more and more charge on, the potential would go up higher, and the amount of charge you can put on there for a given potential is the capacitance, which goes as the size of the sphere. So let's talk about the energy. We'll take a parallel plate capacitor here. We want to know what kind of energy is stored when we charge the capacitor. Remember, if we apply Gauss's law, which we've done before, we can take the pillbox shown here, so area A, and then with all the symmetry we have the field outside, so the field between the plates, times this area here, and then the other side of the pillbox is inside the conductor, so E equals 0. So here's the integral over the pillbox. We get this quantity here. That's Q inside over epsilon naught, which is sigma A over epsilon naught, which gives us this expression which we keep deriving. I just want to point out that when you do parallel plates to get this quantity here, so you get the charge on this side of the conductor, that's 2 times what you would get if you had a charge sheet. So if this were all positive charge with a density sigma, you get half the field on this side and you get half over here. So this field here is not as intense as this one here. So for the same sigma, you get more field between the plates than you would for a charge sheet. You remember that we had before the energy density of a field given by 1/2 epsilon naught E squared. So that's the energy density of an E field. If we take this parallel plate capacitor, then the total energy that will be given by producing this field would be the energy density times the volume. Well, the volume is just the area times the spacing. So that's where the E field exists. And here's our energy density right here. So if we go back and substitute in for our E field, which remember was sigma over epsilon naught, so here's our E field here. Here's epsilon 0. Here's A times D. So this expression here gives us our full electrostatic energy. Called it potential energy, in this case the field energy. Simplify, we end up with 1/2 sigma squared over epsilon naught, and then times A times D. But remember, sigma is Q over A, so putting that in, here's Q over A, there's our sigma squared, and then simplifying again, we end up with this expression here, 1/2 Q squared, and then notice right here, notice this expression right here. That's the capacitance of the parallel plate system. So here's C. We can substitute, this is 1 over C, excuse me, and so we substitute in and we get the electrostatic energy is 1/2 Q squared over C, which means that it took this much energy to put this charge onto the capacitor. That's the work done in order to charge up the capacitor. So if we had a battery, that's the work that the battery would have to do in order to get the charge out onto that plate. Okay, so if we use Q equals CV, we can eliminate Q, we can eliminate C. And so we'd end up with these expressions here. So here's the one that we derived, but here are 2 others, and you should remember all 3 of these. So you would have U is QV over 2 or 1/2 CV squared. All 3 of these are useful expressions. From an earlier lecture, we found the energy due to a uniformly charged spherical shell, which is like the isolated sphere that we just did. So let's look at a review of sigma was equal to be like the Q on the sphere over 4 pi r squared, the area, and we found the potential to be kq over r, and we found the electrostatic energy by using an expression that looked like rho v d tau, but we changed it to a surface integral here. This is a sheet of charge, not a bulk charge. But this expression here gives you the total electrostatic energy if you charge this sphere up to a surface density sigma. The net result was that the electrostatic energy for this sphere, so to bring charge from infinity and put it on this sphere, is equal to this quantity here. This was derived with no knowledge of capacitance of an isolated conductor. Now we know the capacitance of the conductor. So this is the sphere, and here's our value, 4 pi epsilon naught r. Use one of our equations. Let's use this one right here. It's 1/2 q squared over c. C is 4 pi epsilon r, so we put that down here. Here's our q squared, and just crank and grind. 4 pi epsilon naught here is a k. 1 over this is a k. So we end up with kq squared over 2r. So if you forgive capital versus little q, you can see that those are the same. So using capacitance, we can calculate the energy of the field, or you can take this energy of the field and say that's the work done to put the charge q onto the capacitor. Either way, you'll get the same thing. That's a neat result that you'll be using in the future.